Good afternoon to you all. This is great to be talking here at the H2O conference, bringing machine learning to bear in applications. I'm going to focus on, like Ben said, I'm from the engineering side of the family. I'm going to focus on how do you integrate machine learning with applications and make them more predictable, more intelligent in nature, and how do you make this repeatable? That's the core area of my focus today. Why is this important? I believe if you look at the way it's changing, you and Sri this morning talked about a new term called dataware, where data, hardware, and applications are coming together to start making better applications, better processes, the speeds in the marketplace, everything is coming together. So when we started looking at it about three and a half years ago, started building applications, we started looking at all the accelerators in three different vectors. Like, what are the accelerators on the hardware side? If people are watching AWS reInvent right now, serverless is getting thrown around quite a bit, right? So what is serverless? And if you're following that, the next big thing is coming up is fog computing. Stuff like that is happening on the hardware side, where hardware accelerators are driving a lot of speed, low storage, and quite a lot of techniques are coming in from in-memory data grids. The industry is now flooded with a lot of in-memory data grid solutions. Similarly, on the software side, cloud obviously stands out. A lot of efficiencies are coming from software-defined networks, enabled for between regions, computes, and all that stuff. But I think the vector, this gets quite a bit discussed on the machine learning side as well. We are here, we are learning a lot about machine learning. Obviously, all the advances you see from machine learning is very clear in the marketplace, right? So you're now, if you're able to tie all of these things together and make them applicable in real-time applications, things that get thrown around is obviously fraud applications, your ability to predict real-time, all of these things are the applications which gets built in the financial industry space. But making this very repeatable and making it go across the vector, across all the applications is where the focus for us is, at least. Right? We want to make sure that every engineer has an access to machine learning and has the ability to integrate that into the applications as well. When we look at it, I start looking at it from where are we from an application perspective. Again, I'm only speaking in engineering context. Where did we start and how has this progressed, right? So we start, most of the companies which we have in place, we work with business rules. Right? Business rules has become the way to externalize how business wanted to take control on how they want the software to behave or the programs to behave, and how do they want to manage that, reduce the time to market because they have the control on that space. But the challenges with business rules are they're mostly procedural, right? So to make it much more parallel, there are a lot of complexities involved in it. And most of the times over a period of time, you tend to make it more complicated because they get contradictory and they get into an indefinite path of rules. Then control goes back to the programmers. They are the ones who need to resolve through examples, through test cases, how do you make it happen? And in essence, there is no feedback loop, right? So one of the things which you have challenges is how do I get feedback on these business rules and how do I make it much more adaptable to change and make it quick to market, keep that whole mojo about being time to market as a key focus to this. So when we start looking at it, one of the applications we are trying to re-platform is a traditional application which has been around there for 30 years, which focuses on inference rules to match records and stuff like that. So we started looking at it and figured out that by applying machine learning as a core learning, we're able to build predictive applications. And in my own tenure within Capital One, I've done this about 3 or 4 times now, where I'm able to build these applications repeatedly, where we're able to take advantages of the software, hardware, and machine learning advances on how do you build these. So when I started looking at it, I just started jotting down some experiences I have on what did we do, right? So the first thing which we did was look at where do we start from. We started off saying that we want to look at machine learning and artificial intelligence into the business applications in place of heuristics. Heuristics being your business role applications. Can we start making machine learning part of that and make that as part of your ecosystem? What it provides us is you now are able to run more rules against a wide array of data. You are able to independently train the model and then apply that in production in a very trial and error fashion and make that again, very, very repeatable in nature. It also considers all interaction points, and it gives you all the anomalies. I'm sure we have seen quite a bit of the rate under curve, all the things which you get, the false positives. I'll cover our false positive, false negative use case in embedded, but all of those things are what enables in machine learning. The key point for me is about the continuous learning, right? So how do we get, there is quite a lot of things which we apply. We talk about supervised, unsupervised learning, but I think the more important for me is around once you get the model running in production, once you get heuristics built out of the model, the human is still looking at the model and they're still making some choices on these output of this model. How do we take it back to the model as inputs? That's where we worked quite a bit with the H2O team in building that feedback processes into the model learning and model execution. That's where I believe by taking it all the way to the applications is going to help us build better applications and much more intelligent applications in the future. The big thing when I talk from being a data engineer, I definitely want to touch on data management a little bit. One of the key things on any of the data management aspects is around data lineage and data quality. You definitely want to know what data went into the model, how did it score, and also understand the quality of the data, right? So this skewed data, or is it the data which I expect to see? There are, obviously, you talk about ensemble of models, a model governing a model. So there are a lot of other techniques you can apply on when a real-time model gets executed in production, the output of the model, if you start seeing the change in behavior, how quickly can you predict what is happening with this behavior? So there's a lot of heuristics you can build around these techniques, right? It's the same technique you're applying for the application, you're applying it on the monitoring side as well. It just becomes a very closed loop of learning and adapting to changes through machine learning. As I said, I'll cover the false positives in a minute on how did we come to about on building these false positives versus false negatives in this thing. Why, again, when we talk about it, when I look at this, why now is around, I think we are obviously in an open source machine learning conference. Some of the benefits we see here, it's, I think quite a lot of things was already covered on the contributing back to the community and cultivating in-house expertise. It's really bringing back the control to the company itself. Now you own, you're not bound by what vendor provides you. Typically, when you work with a vendor software, there are a lot of boundaries which you have, and you have to fine-tune those boundaries to enable your businesses, and you're modifying your business processes to adapt to those boundaries. But what I would focus on, though, is when you bring on the transformation, which we talk about from an open source perspective, is the enterprises, like most of the enterprises are used to tooling. Like if I go to any closed course vendor, they provide a lot of tooling, and that's what people are used to. Any new graduates who come into play, they do get trained on open source, but they get trained on some of the existing tooling within the marketplace, and that's what they're familiar with. So there is a paradigm shift on how do you bring this to bear, but it's mostly selling point, obviously, is on automation, DevOps, cutting edge, and in-house expertise. And if you're able to build these together in a fashion that it's able to adopt in your enterprise, I'm sure we can start building a lot of these predictive applications and enable the enterprise capabilities. What I adopt is some few core principles on how do we integrate it, right? So I just keep it into 5 basic principles which I have adopted in the way I build these things. Obviously, it has to be easy to use. If it's very difficult, if it gets very complex for the mass population on the engineering side, it's just a barrier of entry. There is much more easier ways to skin the cat, and getting engineers to solve for this doesn't work, right? So you're in an agile mode. You need to produce work every 2 weeks. If that is not easy to build, it just doesn't cut it. For us to be at scale, it has to be highly efficient and scalable. Meaning, how do we, obviously, we spend a lot of time learning about driverless AI this week, but efficiency gets built in by modularizing it and really loosely coupling the architecture, right? So we are very thoroughly do a lot of design work up front. Obviously, we leverage a lot of help doing the design work, but to make it highly scalable and highly efficient is part of the process. If you cannot scale it, and if you cannot modularize it, you probably want to break it down in more chunks and getting it. That's one of the principles we have adopted effectively in building those. The other one, why I like part of working with H2O, is very platform agnostic. If I want to run this in any environment, I can take the model and just deploy it and able to run it. I can bring the data to H2O. Now I'm able to scale it out on-prem. I'm able to do that on AWS. I can create my own cluster if I need to. There are quite a lot of capabilities which gives me that ability to do that. By again, making it highly efficient and agnostic helps me to bring a lot more developers onto the table. Now they can play with their choice of technologies to work through this. The governance is also part of our fabric. It's very important when we look at open sources. We hear about a lot of, I mentioned fraud as a use case, security breaches, and all that stuff. Before coming onto this project, I had built a security system where when we look at governance, I talked about lineage and data quality, but it's more important that it's part of your fabric. It includes security, who gets access to the data, who touches the data, is the data, obviously we use the ontology term which has the as-reported modified data. So with storage becoming cheap, there is a lot of data which you can store, but you also have to store it with intelligence, right? So did the data get changed? Who changed it? And those kinds of things. So governance is a key part of our fabric. We do, for every application we write, we do have a governance model built into it so that it passes the audit, it passes all the other required nature of it. So these are some of the principles which we have in place. At least these are the principles I've adopted in integrating software development with. I used to be a big heuristics fan. Now I've shifted over to machine learning. But this has stayed with me for a long time. And how do we build these applications? All right. So this is a simple example of how do we get there. These are some of the example of the model findings, and I'm just showing one of the models which is here. But what I want to highlight here is how did we get there, right? So we wanted to start the model building with an existing behavior which is there in the ecosystem, rather than trying to find out that gold mine somewhere else, right? You really need to start building on something which you're familiar with and something you can put your arms around and say, at least that's my belief, that you need to start to learn to trust the system. How do you build this trust in the ecosystem? So we started building that with initial existing system behaviors and see if we can model that. We modeled that with about 50 million records, and that completed within our 3 hours, and we were able to repeat this as many times as we wanted. I mentioned Agile earlier, so to make it very repetitive, make it much more predictable with the 5 principles which I just shared, this becomes such a repeatable process. It enabled us to start building trust, confidence within our ecosystem, show the lineage, show the data quality. We probably produced many such graphs and shared with our stakeholders to get their buy-in to take this all the way to production. I'm just showing here as the random forest algorithm, but we did spend quite a lot of other algorithms as well. Before we picked up on the model and algorithm, we worked on what is the feature set, right? So how do you vectorize the feature set? So that's part of what we were trying to do, because as data preparation, it's very, I'll have a slide here on the steps which we take from a pipeline perspective. So streamlining the data preparation, data munging, which goes into the model, is also very critical to build the repeatable process. That comes from the existing system. From the existing systems, you can learn what features are very important, so that we can start with those features before we go out in the market and do much bigger, broader things beyond what is available. This is a simple process flow. Interestingly, I do have business rules at the bottom. So we are not taking business rules away, per se. It is a way to say that that's a feedback loop, which we have built into the records. So we still want to have that feedback loop, which I was mentioning earlier, into the ecosystem. So we do manage the feedback loops through the business processes. But if you look at it, the pipeline before the matching and after matching is where that pipeline can be transactional, so one record at a time, or it could be in a batch mode where it gives you a huge set of data to be processed into the ecosystem. This is where the portability of the software helps. So we are able to manage the portability and still process record by record to get some of these capabilities. In here, what we are showing is a source record is coming in. I will explain the number 2 in a second about search keys. That's the candidate pool which gets pulled in to match against the source record to see what anomalies can be built on top of these things. And when the business rules helps you to gauge if this is within the parameter of acceptance, can we let it through, or should we put this through into a different bucket? And if you do put it in a different bucket, if somebody is looking at it and they make a judgment on it, that goes back into the model as a feedback loop. So the next time around, you are aware of those decisions, and that's where we can build an extensive feedback loop around it. But to bring it back to what the source record is still one record at a time, right? We're still bringing it to a transaction process. We are bringing in a record and then comparing it against the database. And we want to do it at a very, again, we are talking about transaction systems, right? So we are talking about real-time systems within milliseconds. Our model at this point runs in close to 40, 45 milliseconds in a transaction, or even less than that. I'm going to look at Chris. Chris can help me with what that is, but that's where the model, our execution on the model is in the millisecond range and optimized for running that. But the training takes, like I said, it takes 3 hours for training the model. But once we deploy it into production, it's highly optimized to run at scale for whatever transaction throughputs which we have. Skip the slide. All right. Okay. I did want to spend some time here on the searching and indexing on what it is. So this was kind of what we were working on, and how do you think about applying machine learning, right? So if you put it into this matrix of accuracy, performance, and what is your application needs? What do you have as a need? For us, it was about going after performance, right? So you don't want to be slow in a real-time application mode. So that's why we added business rules to manage any inaccuracies in the data, to have alternate workflows to it. So we looked at it and we said, if you want to be accurate, you need to bring all the records. You should not have any missing records to be compared. And the performance is going to be very, very slow. It's going to compare against all possible combinations, and it takes a lot of time. It's probably in the order of minutes than hours. But it's a still high degree of performance which you're going to have, and that's not feasible in the real-time systems. So what we did was we created an intelligent searching of records. So we have, I mentioned about feature extraction and vectorizing the features. So we vectorize the features and we index all the vectors along with the data. So we use a taxonomy to say this is the input record, this is the raw data, and these are the vectorized attachments to the raw data. So we have a way to index all the vector components, and that's what we give to the model as feature comparison to run these predictability. So what it helps us is to get a candidate pool which is highly accurate. It might not have all the records, but it's highly accurate for us to run the machine learning model against it. So we saw a north of 99.7% accuracy when we applied this technique, and the other differences, we could go back to the human interaction, fix it, and bring it back to the model. And we were able to iterate through this very, very quickly. What we were replacing was a 30-year-old application, which was built over 30 years. And this took us about 6 to 8 weeks to prove to our business and our stakeholders that we can build this with high degree of accuracy without having to reinvest into that product. And also run it in real time, because we do have that high degree of scalability and concurrency needs on the real-time market, as real-time space as well. So this is kind of the iterative approach. You've probably seen it. I saw Sri had this as a 3-dimensional vector on the slide. Obviously, it stops with the data extraction, the parsing, the feature selection, model comparison, model management, and the deployment of it. This process is very iterative for us. We want to make sure we built it with the transactional system in mind than the data system in mind. So we want to make this work in the transaction system. So the data extractors, the features or modeled against very minimalistic set of data being available than having all the data available. So this goes back to my earlier comment about you need to spend time designing your application for the needs you have, and then help the data scientists to get them the models you need to run on the applications. And if you don't join them together and work together as a single unit, this takes a longer process. So for us, it took roughly about 6 months to take all of this to production. And we are able to repeat this continuously now. At this point in time, this is a continuous process for us. So why H2O? So for me, it's really comes down to I work with them to add algorithms which is missing. So PDB got added after we started. We have some distance comparators right now within the platform. So we've been able to add those in to the platform. It integrates pretty well between data scientists, data engineers. It has a Python utility tool. It has obviously Scala, Java, all of those easy to use platform. It's pretty robust. It's powerful. I've not had any performance issues, touch wood, so far. It performs to expectation in a scalable environment. It is very predictable in terms of what I get from H2O. I think it speaks for itself being intuitive and powerful. So it's also like the automation. I'm sure we are all hitting the DevOps along with big data, machine learning, DevOps. We are looking at DevSecOps as the way forward, security being part of it. I mentioned being well managed is a very critical part of our fabric. So DevSecOps is what it is. It helps us to integrate all the available tools in the enterprise effectively to meet our governance and regulatory needs, right? Because of the modular ability of H2O, we are able to use the same process for both training the model with production data and on the application side as well. I already spoke about the highly portable nature of it. We obviously use it in Spark, Hadoop, and plain old Java. Now it's called Mojo, right? So model-only Java object. It's still a Java object for us, which makes it, you can put it behind an API. You can integrate with your Java applications. You can integrate with any Python or any library for that matter, as long as you have the repeatable process separated out from data extraction to feature selection, and you make that repeatable as well, right? So one thing which we learned, and I would share, the model is going to give you an output. You like it or not, it's up to you to decide. It's always going to give you an output, right? So you want to make sure that you do have the right people looking at the model to say the output it gives you is the output you're looking for the application. You don't want to just put any model. Every model is going to give you an output. And every model is going to give you a threshold. Will it work for you? That's where you want to spend time. So if you take care of making all the other pieces repeatable, the model piece, it is cumbersome. I wouldn't say it's not cumbersome, but it's not as difficult as it used to be to integrate with application. It's now become fairly easy and straightforward to integrate that with your application stack. That's all I have for today. Thank you.
All right, so we've got a bit of time for questions for Karthik. So get on Slido and ask your questions away. I'm going to go check the app right now, see if there's any, and get the first one up there.
What is an average turnaround time on model retraining cycle? It's a good question. It really depends on the type of model and the complexity of the model you're trying to build. And the model itself, at least in the regulatory environment, has got multiple scale to it. Is it highly significant, or what is the risk attached to the model? It depends on the model and the risk attached to it, the cycle time. In typical process, we should be able to cycle through if you have all the other pieces of data munging and other pieces in place, model is just executing against the data. So we are able to bring data in real time to execute the model as the new data comes in and predict against the behavior. And the behaviors are published in a training environment. So it's everybody to access that behavior. So once we identify the model, once we build the model in, you can run an ensemble of model to compare against it. But that environment is already set up by the engineers to get the data in, understand the features, and putting it in. So I think the real question is how long it takes to add new features, right? So if you want to vectorize new features, that takes time. If the data is not available to get the data in and get it to repeatable and understand the feature selection, I would say feature selection, feature extraction is probably the longer pole in the tent than the cycle time for the model itself.
Great. Got some other ones?
Okay, how do you create recent codes for ML models? I'm not a data scientist. Like I said, I have an engineering background. But that to me is labeling the output of the models, right? So I might be totally off, and I'll take that with a grain of salt. But it's really about how do you label it, right? So this I would feel this is part of the human input into the model on what type of labels you're trying to assign to the predictions you're trying to create. Because the model itself, from a taxonomy perspective, it has the as-reported data, it has the derived data, which is the vectorized data I talked about, and then you're labeling the data based on the type of predictions you're trying to create. And how you label the data is part of the business application, which we will use to label it, right? So that's how you're going to cluster that data together. Hope that's what it means. If not, I'll take the additional question to that. How much data do you need to access in runtime? From a transaction perspective, your transaction is dependent on the data which is coming in. If you look at the transactions itself, I don't think each transaction is not in the petabyte scale. Right? Each transaction is not even in the terabyte scale. Each transaction is limited to a handful of data sets. But based on the transaction, you are going to hit a petabyte scale database to get related records for you to compare against the model to predict on the model. That's where the intelligent searching is coming in. So when the data comes in, we apply all the vectorization on the data to help look up the indexes. We create the indexes on the fly, and we use the indexes to go hit the database to get the relevant false positives or relevant candidate pools, like I showed in the slide, to apply the model against. So in any point in time, it's probably in the order of gigabytes per transaction, not in the terabyte scale. If you model it beyond that, the system is going to have performance challenges. That's probably where you want to govern that better. That's a great question. My experience in working, we have to work with our regulators. The regulators are looking at examples, and it's more, I mean, like I said, this industry, we were, like I'm replacing a model which has been 30 years around, right? So what regulators had back then is what went in and what got out. It really comes back to how are you able to explain the input and output. As long as the input and output is correct and it's very consistent, everything else becomes learning material. Keeping it simple really helps, especially when you're working with regulators. If you try to complicate it with a lot of technology-based things into it, I think that's what opens up to the questions, right? So at least in my experience, I think keeping it really, really simple has really helped to keep regulators happy.
All right, let's give Karthik a hand.
Thank you.